Okay, it's my pleasure today to introduce Isaac Upsal, who is our seminar speaker today. So Isaac is a postdoc right now at Brookhaven National Lab. He actually graduated from Ohio State University, and as a graduate student, he was one of the PAs on a paper that we'll be hearing more about today, which was quite exciting, and that's what's hanging off my door, really, because I love the picture. Isaac not only has been looking into vorticity in heavy ion collisions, which is quite a spectacular thing to look at and has quite some very interesting physics implications. He's also very much involved in STAR's preparations for a forward program, and is playing a key role in that as well. Let me see. I mean, we're going to hear more about the polarization in a second. Isaac also worked on one of the detectors, the event plane detector, which was another detector that is now playing an extremely important role in the beam energy scans, one of our trigger detectors. And so he's been with STAR from graduate student on, maybe already before that. And so it's a pleasure for me to introduce somebody who knows STAR very well, but also who is very familiar with some of its interesting, if not very interesting programs. So without further, I'll give it to Isaac. And Isaac, take it away.
Okay, so I'll be talking about vorticity and polarization measurements. This is a relatively grand title, but it'll be a little bit more focused on one measurement just to give a sense of how it works. So the measurement, if it's about one measure, I'll talk about multiple different multiple experiments, but this first measurement was done at STAR, which is 6 o'clock on the RHIC ring. It's the last surviving detector, although we'll have S-Phoenix soon. And it really takes advantage of some of the unique features of STAR and RHIC. Instead of just jumping in right away, because I want to give just a little bit of a context about the field. So at RHIC is a collider. We collide heavy atomic nuclei and also protons, although this will be focused on the heavy ion physics. So in the first, just right after the Big Bang, the universe was in this state of deconfined quarks and gluons called the Quark Gluon Plasma. It's very hot and dense and too hot to form hadrons. And you have a Big Bang expansion picture that we can get from WMAP and sort of look back. Of course, WMAP, you can only see to the electromagnetic freeze out. So you don't actually see this earlier stage of the universe, but it's there. So we have a picture here with degeneracy and you can see this transition point. So this is the QCD transition, where you have deconfined quarks and gluons freezing out into hadrons. And in heavy ion collision physics, we do something, basically we do the same thing, except at much smaller scales, of course. So this is some lumpy energy density distribution that's left over from a heavy ion collision. It expands and cools and hadronizes. And you get sort of a chemical freeze out at the hadronization, or after the hadronization, I should say, where you can still have some particles interacting with each other to change the composition of particles at the end. And then you have a kinetic freeze out where particles cease interacting altogether and then they stream into our detectors. So this is a detector view at the end here. But of course, that's a huge timescale difference. So this was this can be calculated in um, uh, lattice QCD, and you see a similar transition point in the degeneracy, which indicates a new state of matter and this melting into this quark gluon plasma. And you get a rough temperature of around 150 MeV for this transition point. It depends on a couple things. So it depends, for example, on the left, we have a plot of temperature versus baryochemical potential. So this about 150 MeV is where you have this temperature line. The baryochemical potential is basically just the net number of the baryon, like baryon number. So net baryon number. So nuclear matter is at 1 GeV, normal normal nucleons. So like a proton is 1 GeV. So that's this dot you see at the bottom left where it says, or sorry, bottom here where it says nuclear matter. And up at the very far nuclear matter region, you have things like neutron stars and some potentially quite interesting phases of matter. But mostly what we're concerned about at RHIC is the sort of left-hand part of this plot where if you go to top RHIC energy, or you also do these collisions with lead at the LHC, you're in the smooth crossover. So in that case, there isn't a first order phase transition. But you do have a QGP where it's very hot and it freezes out into hadrons as it cools and crosses this line. It turns out we can change the initial baryon density by changing the energy of the collision. So as you go down in energy, you're decreasing the initial temperature and increasing the baryochemical potential at the same time. I'm not going to talk about this, but there is expected to be a critical point in the first order phase transition, which are also very interesting to the field. In principle, there was some expectation that this could have something to do with polarization, although I think that is not really expected anymore. So the QGP is a very unique fluid. It's a very nearly a perfect fluid. It's got very low viscosity, and of course it's a very high temperature, something of the hottest temperatures we can get on Earth. So it's got a couple superlatives to it. And here's another cartoon. This one gives a clearer picture of sort of the relevant time. You might be interested in, so this is looking sideways. You see these Lorentz contracted nuclei that are like pancakes hitting each other. Here they're hitting each other off center, which is just something that happens, right? We can't control how they hit, but we can control which ones we look at. So this deposits some initial energy density, which is a pre-equilibrium dynamics is something which is very difficult in the theory, and it's not something which is very well constrained. They have various parameterizations of it. Then you have a QGP phase, which is commonly modeled with hydrodynamics, although there's other models. Then these particles hadronize, and you have a hadron gas where you just have a sort of you just look at the particles after a couple Fermi, and you have them collide with each other and do a microscopic calculation, and then they free stream into the detector. So it's much like what I showed before. And here's a video of this happening where you can see this QGP develop and then cool. So once you have the initial conditions, it's not, I mean, it's difficult, perhaps computationally, but it's not theoretically too difficult to solve the hydrodynamic equations and evolve this fluid. There are, of course, unknowns like the viscosity, the shear and bulk viscosity, and various other things. And some of these we can get, some things you get the equation of state from a lattice QCD calculation, but we really want to understand the dynamics, and that has to be modeled. So I've mentioned this particleization. When the matter becomes cool enough at the edges, you need to start emitting particles from this fluid. And naturally, you want these emitted particles to reflect the properties of the fluid cell. Like if you just take an infinitesimal sphere, just draw that somewhere. You want the particles that come from that to have some reality to them. So they should reflect the properties of the fluid cell. And so you usually look at chemical potentials and collective velocities. So the collective velocities will give you the momentum distribution, and the chemical potentials will give you the particle distribution. You know, for example, the net strangeness or baryon number, that sort of thing. I don't have the second slide here. But there's another thing which can be part of this, which is that there can be some net angular momentum, which can work as an chemical potential as well. You can imagine if you have some spinning fluid cell, the distributions at the end should look like that as well. So if we have some off-center collision like this, you have these targets which go down the beam pipe basically, but they get detected by detectors at the end, like the EPD, which Frank mentioned in the beginning. And so at mid rapidity, you have this net angular momentum of the system, and some fraction of this, most of it is going to go with these spectators, these circles that stay hadrons and break up into hadrons, but they don't stay as nuclei. But some fraction of that angular momentum is going to get possibly transferred to mid rapidity, which is to say all of this matter here. And if so, we want to know how this maybe gets distributed thermally, if it gets distributed thermally, because this is at high enough temperatures, this all lives long enough to become a thermalized distribution. Thus, the hydro works. And we want to know how this affects fluid and transport, and how it manifests itself in data, and what sort of effects it might have on the models. So one other thing to note is that these spectators are actually charged, because so we take gold, it's got a net charge once you strip away all the electrons. So there happens to be a magnetic field that's very, very strong that points in the same direction as the angular momentum, but it also dies off really quick. I'll talk about that later, but that could have some effect. So particularly as you go down in energies, as I said, you have some finite baryochemical potential, which is deposited at mid-rapidity. So you have something that we call stopping. At very high energies, the nuclei will just pass through each other and deposit sort of this, it'll just create a bunch of energy density where the collision happened. But the baryons themselves will just pass through it and go down the beam pipe, as you might see at the LHC, for example. So you get more of this particle stopping at low energies, and these can deposit momentum according to the spatial distribution of the angular momentum. And this is manifested in various ways, but you see that, I'll go back a slide. Particles will also flow, they'll move along the direction of these spectators, and that effect is large at low energies. At least in mid-rapidity, that's where we make our measurement. The star acceptance is ±1 in eta, so it's really a mid-rapidity detector. And so if you go down in energy, you can kind of see some dynamics that would be very high rapidity for very high energy collisions. So more stopping means more charge, which also includes things like, so that's some baryon number is a charge also. But more electrical charge, which means greater conductivity. And because of Lenz's law, if you have conductivity and this magnetic field I talked about, you can have a longer lived magnetic field. It would be weaker at the start, but it might live longer, which I'll get back to later. So here's just some cartoons of vortexes. Just because you have a vortex doesn't mean that you'll necessarily have a vorticity at a given point. For example, this irrotational vortex is kind of a pathological example where the orange dots are not rotating around their centers, but the blue dots are. And what you probably have is something in a real fluid with viscosity somewhere in between these. So now if we talk about the heavy ion collisions.
Isaac, sorry.
Yeah.
Can we go back to that just so it's like, you're saying one of them has vorticity and one of them does not?
One of them, so for this one, what I mean is that if you look at this red dot here,
okay,
and you watch and you look at the, sorry, I didn't explain this really at all. You look at the relative velocity field, they cancel out. So if you look at the vorticity at this point, if you imagine this as a fluid cell, it wouldn't have any vorticity.
okay.
The system itself has vorticity because of here. If you integrate around here, around the center point, you'll get something. But if you take any point outside of that, you won't.
So you're saying the vorticity would be like a delta function at the central point,
Right.
But everywhere else it's, whereas on the left, you're saying there is a vorticity because, well, I see.
Because there is some sort of local shear. There's always a relative velocity between sort of the nearer and the further one,
right.
And these add up.
Sorry, and what are the bottom right pair of panels then with the?
Oh, so the bottom right. So this is like looking at this fluid cell as it rotates around the middle one, and you can see the blue one is actually rotating about its axis, whereas the orange ones do not.
Oh,
so
okay.
if you have
the white line is that's what I'm supposed to look at. The
yeah,
the white line
is to
changing
indicate
orientation on the left but not on the right.
Yeah.
Got it. Thank you.
Yeah, so those are just sort of examples of possible, so these are just examples of possible velocity fields. We can imagine all sorts of fields, but what you expect if you actually have a sort of flow field is to have some, in a heavy ion collision, since there are these gradients in the velocity fields, you expect to have some vorticity, and that will in principle depend on things like, how strong this is depends on something like the shear viscosity in principle, although models seem to show that it doesn't depend that much as certain flow parameters do. But you expect some local vortex generation being due to baryon stopping, which gets dissipated to the field, to the fluid at a larger scale. You can imagine if there is no baryon stopping, or if there is no at very, very high energies, let's say infinitely high energies, you maybe make a vortex at every point where a baryon was, but they average to zero. But the important thing here is that you have a sort of slowing down at lower energies where these things can be dissipated. And you need some, if you have a really perfect fluid with no viscosity, you won't get any net vorticity. You might get some vorticity in spots, but you won't get net vorticity. So this is a really fundamental part of the fluid and its generation. The vorticity is part of the second order hydrodynamic equations. It just wasn't really considered for most models for a lot of time. This, in fact, had been proposed that you could look at this some time ago. So in 2004, here's a paper that suggests that you could look at this for various particles, and a measurement was done at star. And so there's a bunch more papers since. So let's say this was before we got a non-trivial result. There had been an active search for this, where there was a measurement in star in 2007, which found no polarization, which I'll talk about again. But the theory had been continuing. So if I want to look at, I didn't actually have, okay, so I'll talk about why these are lambdas and anti-lambdas in a moment, which is the measurement that's actually done. But if you imagine these particles as spinning tops, where the sort of top of the little part where you would hold is indicative of the direction of the spin, you expect that basically all the baryons should have a similar contribution, or at least all the spin 1/2 baryons should have the similar contribution where their angular momentum aligns with their spin aligns on average with the angular momentum of the system. That's actually dependent, like proportional to the spin of the particle, intrinsic spin of the particle. But if they're frozen out from the same space, there shouldn't be a really species dependence, at least at first. And there's also a possibility for electromagnetic. So the magnetic field points in the opposite direction. If we think about lambdas and anti-lambdas, or any particle-antiparticle pair, they're going to have opposite magnetic moments. And so if there was no angular momentum in the system and only a magnetic field, you would have a sort of version of this where the lambdas and anti-lambdas point in opposite directions in terms of their net spin is along the magnetic field or opposite to the magnetic field. It happens that lambdas have negative magnetic moments, so they would be opposite the magnetic field. There's also a third contribution, which I think I'm just going to skip for now.
Sorry.
Go ahead.
So before you go on and to talk about the measurements, maybe I just ask one more question about vorticity to see if I'm following. So suppose that the collision were perfectly head-on with zero impact parameter, and then for that rare occasion, there would be no angular momentum. Is that right?
Right.
And then in that case, would there also be zero vorticity?
Yeah, on average. You might get little vortices here and there, but if it's really head-on, and of course, okay, so at some point it's lumpy, right? And I don't know but if it's perfectly head-on, if there's no angular momentum.
So my gold nuclei are perfect spheres.
Right. Yeah. So there would be no net vorticity there.
Okay, and then you're saying, sorry, when you say on average, you mean in principle you could talk about vorticity at different points within the Quark Gluon Plasma, but on average means volume.
Right. And there might be ways of looking at that, but for the most part, we can't measure.
Okay. Okay, that was my other question. Okay, so then the idea now is that for realistic collisions with a non-zero impact parameter, there is some angular momentum, and then from that, presumably one can calculate the predicted vorticity. It's linked to the size of the angular momentum, I suppose.
Yeah.
And now you're going to, okay, great.
Right. So there are various things which contribute to that, but in principle, the idea is actually pretty simple, which is just that if you want to see if the vorticity can be measured, you can just correlate spins to the angular momentum direction. And if you see a positive contribution, then you've seen a polarization. And then, then you worry about the size and whether or not that meets theoretical expectations. So this has an interesting parallel in the Barnett effects, where you take an uncharged object, you rotate it with an angular velocity, and it spontaneously magnetizes. So this was first mentioned in 1915, so they didn't really know about spin, which is an important part of this. And if you think about it, it's actually not, it's not really trivial at all, but it's a measurement that has been made. It's a real effect. And it has a parallel in the Einstein to Haas, where you take a magnetic field and you can induce a rotation. So really what's going on here is you have a net angular momentum in the system, and you have coupling, subatomic coupling to that net angular momentum to make, or that is the spins coupling to that net angular momentum. So you're seeing a sort of effect of polarization. And it's kind of funny, I just put this up because it's kind of funny how a paper in 1915 could start, where you say, in 1909, it occurred to me while thinking about the origins of terrestrial magnetism. It just seems so casual. So this was in Science in 1915. So I said before, I was talking about lambdas. Why do we look at lambdas? And essentially because they are self-analyzing. They have this parity-violating weak decay, where they reveal their polarization by preferentially emitting the daughter proton in the spin direction. So this is something that's been known since the 60s. They really started looking in the late 50s and then measured it in the 60s. Where if you look at so you look at the proton's direction in the lambda's rest frame, the spin is, it follows a distribution which is centered on the spin. And that's what this equation here is showing. So in this equation, alpha is just a number that you measure. So this is not theoretically determined. And in fact, this is kind of an old version of alpha. This is the version of alpha I used. It got updated just a year or two ago in the PDG from some new measurement. But yeah, so this is not something which can be understood in the sense that there's not a theoretical understanding of what alpha should be, but there is an understanding of why it should exist. So,
Isaac, so since I am going now through updating together with Wrong several of these papers that used this variable for alpha with the new one. The new one changed quite a bit compared to what the uncertainty here gives. Do you know why it changed by that much? Just for people, it changed to 0.732, which is really outside the uncertainty given. Do you know what happened here?
So there was a new measurement by the BES collaboration, which does these, I think it's electron-positron collisions. They make lambda anti-lambda pairs. Why it changed is actually a mystery to me, because I've read older publications from the BES collaboration that are consistent with this measurement. And it seems to be the argument is something along the lines of this is a cleaner way to measure than what was done in the 60s and 70s. But I was surprised, I'll just say, that the PDG just updated it to that number, and they haven't explained why. So they don't give an explanation exactly, I guess.
Good, interesting.
Yes, yeah. It's not, I'm not a total expert in this, so I don't want to cast aspersions, but I don't know if I really understand it. So we can measure we measure the spin by looking at the proton's direction in the lambda's rest frame, emitted direction. And then we can measure the angular momentum of the system by looking at the spectators going into forward detectors like the BBCs or the EPD. So these are just scintillator hit detectors that measure protons as they go through. And it'll get you an orientation of the collision. That's what you use for directed flow or this sort of thing. And then otherwise, you just have various prefactors that have to do with the measurement, how you do the measurement. But the polarization you get is a number between 0 and 1 that's a percentage. And so here's a picture of star. I'll try to go through this part kind of quick. we have protons and pions. We reconstruct them in the heart of the detector is the TPC, where we do tracking and some particle identification. And then this forward detector is the BBC. So we get the momentum as measured by the TPC because we have a magnetic field which is bending these charged particles into helices. So by the radius of the helix, you can get the momentum. And then we look at energy loss in the gas of the TPC, and there are characteristic bands for different particles. So we want to reconstruct protons and lambdas to find, protons and pions to get lambdas. So we can see that here, and we also see in the TOF, which Frank is intimately familiar, you see bands for the proton and pion. So cutting around these bands can get you the particles you want. And ultimately, then you do some topological cuts, which is to say you'd cut on things like decay length and the distance the particles get to the primary vertex. So we reconstruct a star with lots of tracks. You point back to a primary vertex where the collision happened, which is so we look how close the proton pion get. They shouldn't be close, for example, because they're secondary. And we try to reconstruct lambdas, and we get a mass peak that looks like this. Here's just a cartoon of these cuts, which I'm going to go forward with. And we can get momentum, impact parameter direction from these two the fragments going to the forward detector. We see some nice anti-correlation here. And this is a 7 GeV. So this is a statistics limited experiment. We really measure over the average of the acceptance. So I'll just kind of look over the math. You get something where the average polarization is this prefactor times the sign. So this is the impact parameter direction as measured by the spectators. And this is the proton's momentum direction angle in the lambda's rest frame. So the star means in the lambda's rest frame. You might think these two are actually sort of in different rest frames, which looks kind of strange. It turns out not to make a very big difference. And then finally divide by the resolution, so how well you can determine this impact parameter direction, which is something that changes with how much the collisions overlap and what energy, and of course what detector you're using. So this is what we get when we measure this, when we correlate the proton's momentum with the angular momentum of the system. And what you have here are these hollow points, these two hollow points here and hollow points here are a measurement STAR did in 2007. I have other versions I've updated that archive because it's been published. But the first sort of positive measurement was these, the 7.7 to 39 GeV in the beam energy scan. There is an anti-lambda point for 7. It's just like right here, and the error bars are really big. You'll see that later. But now we even see a positive measurement at 200 GeV. And you can see that, especially with the 200 GeV, there's this trending downward slope. This may not seem obvious because as you go into higher energies, the net angular momentum is increasing, but the percentage of that angular momentum that gets distributed at mid rapidity decreases. So these are sort of competing effects, and it turns out one of them wins. So the fact that all of these points are above 0, I mean, they're not all statistically above 0, but as a whole they are. That implies a positive vorticity of the system. If the anti-lambda were higher than the lambda, that could imply a magnetic coupling, because if you remember, if there's no magnetic field, if there's no vorticity, the anti-lambdas would align with the magnetic field in principle. Now, in practice, the time matters. So I'll get into this in a moment. So we can use these facts to sort of study more fundamental properties of the system, which is an interesting thing we started looking into when there wasn't too much theoretical input.
Sorry. I'll ask another question.
Is there a question?
Yeah, before you go on. Firstly, can you give me a sense of what is the efficiency of reconstructing the lambdas? Do you see them all or tiny fraction? Just a ballpark.
I'm afraid I can't remember very well. It's not very good. I'll tell you that. Particularly, right, this depends on how we use our cuts, but I think it's like 40%, I think, is a rough idea.
And then the other question was, just so I'm following. So you were trying to ask whether there's a vorticity in the collision, and the net polarization of all of the junk produced in the collision is some proxy for the vorticity. But you're using lambdas because you can figure out their spins from the protons. But I guess some of the polarization is carried by other particles or other hadrons, but you can't figure out their spins.
Right. So we'd expect the proton to be just as polarized as the lambda. I mean, it could be wrong, and the proton could be twice as polarized as the lambda, and there's no way. So we just, for us to know that, so we just use the lambdas as a proxy for similarly spinned baryons.
But I guess, like, if one wanted to be really terrible, could I argue that the polarization that you've measured here in lambdas is compensated by an opposite polarization in whatever else is produced in the collision, and so there's no net vorticity?
Yes.
That would be pretty perverse.
I think that would also be very interesting. So if that were the case, that would be a very interesting scenario as well. But yeah.
I mean, I don't have any reason to expect that. I just want to make sure I understood.
Yeah.
Okay, sounds
good. So what we actually measure is a polarization, and then we try to get some sense of what it means just using relatively simplistic understanding of the collision. That's what's going on in this slide. So we expect the polarization to be drawn from a distribution that depends on sort of basic fundamental particle properties. So this is for all hadrons. You have a baryochemical potential and a baryon number. You have the energy and the temperature. This is the vorticity coupling with the spin of the particle, so omega dot S. And this is the magnetic moment coupling with the magnetic field. Unfortunately, there's a lot of degeneracy in the letters here, so mu is used twice. But for a very small polarization, you might sort of expect, you might be able to sort of simplify this into, just expand out the first term and get that the lambda is proportional to, the polarization of lambdas is proportional to the magnetic. All right, so this is the magnetic moment, and this is the vorticity. So if you were to sort of reverse these equations for the lambda and the anti-lambdas on the right, you can get the vorticity and the magnetic field sort of directly. But this is actually kind of complicated because there's significant feed down effects. So a lot of the lambdas we get are coming from sigmas or cascades or sigma stars, which are themselves polarized. And when it comes to the polarization of a particle which came directly from the collision, this sort of framework would assume that it's only really has to do with the magnetic moment and the spin of the particle, but that the particle itself is otherwise not so important. I mean, it could depend on magnetic, some baryon number or strangeness or something like that, but that would probably more depend on, that would probably have a bigger effect on the distributions. But when it comes to the feed down, that has a more complicated effect. So we did some study about this. I kind of want to sort of speed through this, this part because it's a little bit detailed. But the point is we wanted to look and try to get vorticity directly. This is maybe a little bit, let's see. I'll just say that, oh, whoops, it's not. if we want to extract the vortical component, we have to think about what the particle spins are in the start, and that's proportional to the spin. So we looked at a bunch of higher state particles that decay into lambdas, and most of them are spin 1/2. The sigma stars are spin 3/2. We looked at the most common ones and expect the rest sort of average to 0, but then you have to calculate what percentage of that spin they get. So if you look at like a Clebsch-Gordon table, you can actually calculate from like a sigma 0 that decays into a lambda, what fraction of the spin the lambda gets. And if the sigma has 100% spin, you'll get lambdas with -1/3 on average spin. So this really matters. And for the magnetic component, it matters even more because, well, that part matters just as much, but the beginning part, you have magnetic moments which can depend very strongly on the particles. Let's see, I'll just skip through this and say that you can kind of get a vorticity which is not so different from what I showed before, where you're just getting vorticity from averaging the lambda and the anti-lambda, and magnetic field from taking the difference with some prefactors. So this is kind of a complication, but you get what you expect, which is that the vorticity is sort of, since the lambda and the anti-lambda are pretty obviously above 0, you get some positive thing. For the magnetic moment, you don't get a positive measurement, which is good. So the 7 GeV just has really huge error bars, and so I don't think that should be taken too seriously. I'm going a bit slower than I expected. So I'll talk a little bit about theory. So these days, the theory really does calculate the polarization. So comparing to the vorticity is not totally necessary, but at the time we did the measurement, we were trying to get something that compared to the theory. So we extracted this vorticity, and it was, let's say the takeaway, it was on the right order of magnitude. So this is 10% in this calculation at Nika energies. This, you're taking some late time average. It turns out the vorticity decreases the longer the system is alive. So angular momentum is a conserved quantity, vorticity is not. So if the system lives longer, it decreases with time, which is another reason that this high energy which is another reason it's dropping with energy. Let's just say, and it turns out if you do a 3+1G viscous hydrodynamics, you can actually get these values pretty well. So this is a hydrodynamic calculation that really gets the features of the data quite well. And it's really independent. So then there are a couple different calculations that have been done using AMPT and a couple different ones with hydro that are various degrees of realistic, but they can get some features. One of the things I didn't talk about here is actually the hydro. They did some measurements, and well, what they found is that if they change the initial conditions, there's the pre-equilibrium stage of this hydrodynamic calculation, it really changes the polarization a lot. So they found that it's not very sensitive in a systematic study. It's not very sensitive to the shear viscosity, but it is very sensitive to the initial conditions, which are generally pretty poorly constrained for these hydro models. So it gives us an extra sort of lever arm to tune and understand hydrodynamic models, because there are a couple, right? There's always some inputs in there that are coming from, you want them to be coming from data, and they're not really fundamental, because they're not fundamentally understood. It's more like a phenomenology. Now for the magnetic field, since it's 0, there's not too much to say, but it's more or less maybe on the scale you'd expect, although it turns out to be very complicated. There's not really any understood evolution of the magnetic field. At the very early times, it's easy to do that calculation, but how it evolves with time depends on the electrical conductivity. And this is kind of interesting because at the lower energy collisions, you have more charge in the QGP. So it will decay slower. So it might be that this magnetic field's effect on the polarization could increase. But let's just say there's a lot of variables here. But it would be extremely interesting if we can measure this. And it might be maybe something that we could have a contribution to the understanding of in the future, because we're going to be taking, well, in fact, we basically have already finished BES-II. This is a picture of the EPD, which is, as you can see, much more segmented than the BBC. It gets a better event plane resolution. We took a lot of data. Unfortunately, most of it, none of it is produced yet, so we can't analyze it yet. It's not in the data format that we can, as analyzers, use. So that still needs to be waited on. But we've taken the data and we're eager to look at how this affects. This is a comparison of the BBC and the EPD, and you can see that the resolution which the polarization was proportional to is a lot better. In fact, so since it's proportional to resolution, getting twice as much resolution is the same as 4 times the statistics. So it's a really cost-effective upgrade. And you can see what this does to the error bars. I just put the error bars so the shaded region is for BES-II. I mean, I would not take this data point seriously. It's not going to be up there. But what it tells you is that it will tell you if this is just a little anomaly. We might be able to start really getting something which tells us something about the magnetic field. Of course, this could all just be a statistical fluctuation, but we've taken the data, so we're excited to analyze it. And so all in all, what we got is this very high measurement of the vorticity, and it gave us a new superlative for the QGP. So here's some real world comparisons where, the normal vortices you see, even in very highly fast spinning things, are usually something which is less than 1 in terms of inverse seconds. These vortices we're extracting from the data is way up in the order of 10 to the 22, 10 to the 23, which is many orders of magnitude higher than even sort of special laboratory conditions. It's possible that the QGP could have the highest magnetic field ever measured as well. And there are other measurements which are interested in this, and it's just another nice superlative for us to get if we can. I'm going to skip the CME stuff. So there are a couple other measurements that you start thinking about immediately doing, which is, so in our field, you look at the azimuthal dependence. So if something is emitted in plane versus out of plane, maybe I have a better cartoon here. Which is to say, like along this direction of the overlap, along 180 degrees of the impact parameter direction, let's say. So in the impact parameter and 180 degrees, and you add those up, you want to see if the polarization increases relative to that or 90 degrees away. And what we see in the measurement is actually all right, sorry. This is a hydro calculation. It's the hydro calculation that got the data so well before, and expects a smaller polarization in plane than out of plane. But in fact, in the measurement, we see the opposite. In plane polarization is larger than out of plane. So this is a 200 GeV where you really have the statistics to look at it. And this is something where we just see some tension with the theory, and we don't really have an explanation. In fact, the BNL seminar today was talking about this, which is quite interesting. Well, it was talking about the next thing, but I think they're kind of related. This might have something to do with different sources for the polarization, but that's really on the edge of what. So it's something that theory is very interested in right now, but I can't give a definitive answer for why this is happening. There's another source of polarization where, so if we look at this collision, you have elliptical flow, we'd say. So you get more particles being emitted with higher momentum in plane, so along the direction of the impact parameter, than out of the plane, if you're looking at along the beam direction. So, but whenever there's a flow gradient, you can get a vorticity. So you sort of naively expect from this that you'll get some sort of quadrupole structure, where if you look at this segment, your sort of your vorticity is into the screen, and if you look at here, it's out, and then in, and then out. And these would all average to 0, but if you look at it as a function of the emission angle, which was done at 200 GeV again, you actually see a dependence. And this dependence is opposite of what you see in theory. So again, you have some tension with the sign, which is quite a strong tension to have. Yeah. So,
as a for the theory, yeah, this morning actually I asked the similar question to Ian about this, because in the QGP I'm just steering gas, because the QGP can hold the magnetic field created by our heavy-ion collisions. So I'm thinking the origin of the alignment, because in the theory they are mainly considered about the vorticity of the fluid dynamics of the QGP. But I'm thinking if they really take into account the magnetic field into account, because the magnetic field could polarize the quarks and also the gluons. So I'm thinking whether this could make any difference on the theoretical prediction.
Yeah. So it could, as he said, I believe it's possible. So the thing is that we actually have a tidy way of looking at this, which is that the lambda and the anti-lambda have oppositely signed magnetic moments. So if the magnetic field gives a positive polarization for the anti-lambda, it will give a negative polarization for the lambda. So the fact that we measure consistent or near, well, yeah, they're consistent measurements for the lambda and the anti-lambda. I mean, I can't say that it doesn't mean that there's not a magnetic effect, but I think it's fair to say that whatever it is significantly smaller. But the theory is in no shape right now to do full magnetohydrodynamics and answer that question. I mean, it's something we're very interested in, and we would like to do this measurement in beam energy scan 2 to see if we can see a difference in the lambdas and the anti-lambdas. I mean, if we really see this higher, yeah, that would be extremely interesting. But I think you can say that it's not as big of an effect, or they're not being negligent by not including it just off the data, just by the fact that you can see the data. The lambdas are consistent with the anti-lambdas, at least with the error bars we have. But it is something that's relevant ultimately, and it's something that theory is, everyone, let's say, in the field is pretty interested in. Everyone looking at polarization. Some people are working on that pretty directly, but most of the hydrodynamic don't try to do this.
Okay, thank
you. All right. So I'll let's see, I don't think I have a lot of slides left. So we have other measurements. This has excited. So we've got measurements, we've got a measurement in HADES, and we're also doing in the beam energy scan, we have this fixed target, which I'm sure Dan has given a seminar for you guys at one point. We have a fixed target, a little bit of foil here at star. And if we steer the beam, one of the beams into that, we can actually get fixed target collisions at very low energy. 7.7 is as low as we can get at RHIC, because it just becomes too hard to control the beam and get a good rate of collisions. But if we do the fixed target, we can collect data very, very quickly and go to very much lower energies. The acceptance is not built for that, of course, but it turns out star is very good. So the TPC has worked a lot better than anyone expected 20 years ago. And we have added some upgrades with the inner TPC and ETOF, which is RHIC has been also involved with for particle identification. So some of the problems, the acceptance might not be built for it, but it still works quite well. HIC is a fixed target experiment, so they're built for that. And here's, I just want to give some sense also. So there's also in the future, we have NICA and CBM, which will be fixed target experiments that can explore this low energy region in yellow here, which I only want to show the region. I'll talk about the data points here. So the polarization, the fixed target, you've got a preliminary result from HIC here, which actually, I'm a little bit confused because the error bars have changed a bit. The systematic error bars are really huge. So this is the systematic error bar cap, and the statistical errors are quite large. So it's consistent with 0, but it's hard to say if that's really a constraint. We have a fixed target and data point, which has been gone through star preliminary, right? So I can show it right here, which is consistent with the 7 GeV. Yeah, this is with this new alpha that we were talking about before. So it might be interesting to see how this depends on rapidity too, because if you take fixed target at 7 GeV and collider mode at 7, those are different rapidity ranges. That's something that's going to be prove a challenge for how exactly we plot this, because it kind of bothers me that these are in the same, even though they're different rapidity ranges. In principle, the polarization can depend on the rapidity. Elise also did this measurement and got consistent with 0, which seems more or less in the expectation as this is falling so quickly. But it's good to have this point a very high rapidity, a very high collision energy. And finally, I'll just mention that we are planning on doing a forward upgrade in STAR, so we'll get some tracking and calorimetry very far forward. It's not really obvious how easy it will be to measure lambdas, but there's some tension at the forward rapidity. So I mentioned at the fixed target, that might be another way to look at this. But the angular momentum per parton is actually increasing with rapidity. So these orange bands are where this upgrade will be in STAR. So that's just to give a sense of this is from an AMPT calculation. So even though the angular momentum itself might sort of change, might even decrease at different energies, it seems to be uniformly increasing if you look at it per parton. And here are some calculations that show that this polarization should drop very quick. I won't go into the details of what these measurements, what these models are, but they drop really quick, so that even in the forward rapidity range that we expect 2.4 to 4 for this forward upgrade, it should be 0 if we believe these models. And if we look at this model, it's also decreasing. So this is a hydrodynamic calculation, but not quite as quickly. Don't worry about the sign. There's just different things that are being measured, but this is sort of the negative thing. This W shape is proportional to the polarization. This is something I got from asking the authors. They gave me the plot, but they said the initial conditions might not be valid this far forward. So there's some uncertainty theoretically that isn't represented. But here's another hydrodynamic calculation, which shows that vorticity is actually, there's now several different kinds of vorticity, but they're all increasing in the forward region relative to mid-rapidity. So this is also 3D viscous hydro. They use different initial conditions than the plot I just showed. As I said before, polarization has proven to be very useful at constraining the initial conditions, and looking at forward polarization might even be better. So I've got a summary, but I think I'm basically out of time. I'll just say that the polarization, we can measure it. It's quite a new and novel thing, and there's a lot of interest in this. And really what it tells us right now is that we can constrain these models and it just gives us a new, it's just kind of a brand new measurement. We've been doing flow measurements with heavy ion collisions for decades, and it's exciting to have a new thing that we can help constrain the models with. It's a sort of cute thing that we can get a superlative with the most vortical fluid, and in principle we might be able to get a magnetic field, which would be also very interesting and very important for things, novel phenomenon like the chiromagnetic effect, which I'm not going to talk about because it's quite complicated. But I think that's the end.
Thank you very much, Isaac. On behalf of the people that are muted, I applaud. Are there questions for Isaac? I see Yiding, you raised your hand. Go ahead, Yiding.
It's not raising, it's a clapping hand, but I really have a question. So Isaac, did the star have any plan on the measurement of the polarization in the small system? I'm not talking about the proton-proton lab, but like the proton golden, proton lead, or the oxygen, something like that.
Yeah, I mean, I can't imagine it. Oh, so this is something I didn't talk about, but in fact, even comparing, so we took this isobar data, which was ruthenium and zirconium, that's smaller than gold. And just looking at any system size dependence could be interesting because you are changing you're sort of simultaneously changing the angular momentum of the system, but also how long the system lives. So the vorticity is supposed to decrease with how long the system lives. And comparing those things, I think, could be an interesting constraint. So presumably, if you look at something smaller, or at least let's say there are calculations that if you look at a smaller system like copper, it should increase relative to gold. And I think that would be an interesting thing to see. I mentioned the isobar because we have a lot of statistics. We have billions of events for the isobar, and we have a lot of statistics for top energy gold. I am interested in these other systems, so we've taken lots of data. RHIC is very, very versatile. We've taken helium, gold. We're going to take oxygen. I'm sure it'll be measured in oxygen. For these smaller systems, I've thought about it. Is the problem right now, I think, is just that the polarization is so small already in gold that unless the calculation tells me it increases, well, let me say, I think it's interesting, and I hope it will be done. But
yeah, because I ask because for the vortical effect, the vortical polarization effect they talk about for the proton golden or the proton lead collisions, well, theoretically they don't exist, right? For the vortical effect, they don't. But as we know, the magnetic field exists in this collision. So that will be a very interesting comparison between the different systems. Well, I planned to ask another question, but I forgot. Sorry, go on.
I'll just say another complication with these smaller systems is that it becomes harder to measure the angular momentum of the system. So you get hurt in that way too. You get less statistics, less lambdas. We happen to have fewer events. It's a smaller system, so I think you get less angular momentum. But I do think it's an interesting measurement to try to do, at least to a preliminary look at.
Yeah, I remember the last question I asked. So the magnetic field we talk about here is the same the dipole moment we talk about the CME, right? They should be the same thing.
Yeah, right. So the CME, I think one of the things that's really interesting about this measurement also is if you can get the vorticity in the magnetic field, these are things that don't require chiral anything. This is quite simple. One of the big uncertainties when trying to calculate something with the CME is you've got this winding number of the gluons, and you've also got the magnetic field, which is very poorly constrained. I mean, the winding number of the gluons is essentially totally unconstrained. So if you could nail down the magnetic field, it would really give you a much better understanding of how to to make these calculations. And that's also true for the chirovortical effect. So this, since they have some requirements on this chirality, which this measurement doesn't, it's a nice complement to them.
Thank you very much.
Isaac, you showed at some point the polarization, the star preliminary point, which was a fixed target 7 GeV data point, wasn't it?
Yeah, it's a 7.3.
Yeah. Yeah, that's the one, right? Yeah. That still comes with very large uncertainties, and yes, this is preliminary, so this likely will have some conservative estimate at this point. Having data points here that actually can be done with some better uncertainties than what we see in this plot can be useful. And what I'm going to ask you is that with the forward program that you've been working on quite a bit, and the prospect of having that forward system sit there during STARS 2023 and 25 run, does it make sense to look at a fixed target 100 GeV beam that impinges on the target and gives you a 13 GeV fixed target point with high statistics? Only a couple of days.
I think that would be very interesting. Wait a second. So is the fixed target on the wrong side of the detector though?
Is fixed target?
I think the fixed target is on the same. The target is on the same side of as the.
Where's the ETOF? Is the ETOF on the side of the forward program?
No. So the forward upgrade is on the west, unfortunately, and the ETOF's on the east.
There goes that plan. Okay.
Right. I will note for this fixed target point, the 7.3 I think was one of these parasitic ones, so I don't think it has great statistics. And also.
Well, I think the 3 billion events that are planned to be taken in a few weeks from now, they will, and that's at 3 GeV, and that's definitely where expectations are that we could see a more pronounced effect, right? So,
I mean, I did some simulations trying to reconstruct lambdas with the forward upgrade, and let's just say it's not trivial also. So trying to make an argument physics program that is motivated by polarization is difficult. I mean, we'll take 200 GeV data so we can try to do the measurement, but trying to say like we need more beam time for polarization might be a little tough anyway.
Okay, I'm gonna stop the recording, but I will not do that before another round of applause for Isaac, and then there's some time left for people to stay around. So thanks again, Isaac, for an interesting talk, and I'll stop the recording right here.